In this video, I'm going to introduce you to the other significant theorem for calculus in three dimensions, and it's called the divergence theorem. The flux form of Green's theorem allowed us to calculate the amount of a substance that would move through or across a surface. The divergence theorem gives us a different interpretation in order to measure this same type of flow in R3. In the divergence theorem, we will add up all the sources or sinks of the flow throughout the region instead of using flux integrals. But essentially, the divergence theorem is just a three-dimensional version of the flux form of Green's theorem. So I want to review the flux form of Green's theorem. In this theorem, we started with a closed, simple, smooth-oriented curve C in the xy plane, and it served as a boundary for my region R. And I had a vector field given by F is equal to a vector with components Fg, which was differentiable on R. The integral form of the theorem states that the closed integral over C of f dotted with n ds is equal to the double integral over R of f sub x plus g sub y dA, where the left-hand side is the flux across the boundary of R, and the right-hand side gives me the net expansion or contraction of the vector field within R. If we imagine the vector field as fluid flow like we did before, this basically says that the cumulative effect of the sources or sinks of the flow within R is equal to the net flow across the boundary of R. In the divergence theorem, the plane region R that we worked with in Green's theorem becomes an oriented surface S in R3 that encloses a three-dimensional region D. The flux integral in Green's theorem becomes a surface integral over S, and the double integral in Green's theorem becomes a triple integral over D of the three-dimensional divergence. So I may have a region R that is bounded by a curve C that is oriented so that the positive flow is in the counterclockwise direction, and the flux form of Green's theorem for this region said that the closed integral over C of f dotted with n ds is equal to the double integral over R of the divergence of f dA. And I move into three dimensions, I get a three-dimensional region D with a surface S, and my divergence theorem becomes a double integral over S of f dotted with n ds, which is equal to a triple integral over D of the divergence of f dV. If I let f be a vector field whose components have continuous first partial derivatives in a connected and simply connected region D in R3 that is enclosed by a smooth oriented surface S, then the double integral over S of f dotted with n ds is equal to the triple integral over D of the divergence of f dV. This is where n is the unit outward normal vector on S. The left-hand double integral is the flux of the vector field across the boundary. The right-hand triple integral is the cumulative expansion or contraction of the field over the region D. There's a key characteristic of the divergence theorem that I want to mention. In Stokes' theorem, the rotation fields have non-zero curl, but in the divergence theorem, pure rotation fields have a zero divergence. So let's work an example. I want to evaluate both integrals of the divergence theorem for the vector field given by f is equal to a vector with components x squared, y squared, z squared, where D is the set of all points x, y, z, such that the absolute value of x is less than or equal to 1, the absolute value of y is less than or equal to 2, and the absolute value of z is less than or equal to 3. I'm going to first compute the volume integral, and to do that, I need to compute the divergence of f. The divergence of f is f sub x plus g sub y plus h sub z. This is equal to 2x plus 2y plus 2z, which I can write as 2 times the quantity x plus y plus z. So that my triple integral over D of the divergence of f dV is equal to the iterated integral from -1 to 1 of the integral from -2 to 2 of the integral from -3 to 3 of 2 times the quantity x plus y plus z dx dy dz. I compute the innermost integral first, and I get the integral from -1 to 1 of the integral from -2 to 2 of 12 times the quantity x plus y dy dz. This becomes the integral from -1 to 1 of 48x dx, and when I finish that integration, it becomes 0, so that my divergence here is equal to 0. Now I need to evaluate the surface integral. For the rectangular prism I have, we have 6 faces to work with. I'm going to take sides S1 and S2 to be the sides that intersect the x-axis at -1 and 1 respectively. S sub 3 and S sub 4 will be the sides that intersect the y-axis at -2 and 2, and S sub 5 and S sub 6 will be the sides that intersect the z-axis at -3 and 3 respectively. I can sketch my region, which gives me the rectangular prism centered on the origin, where S sub 1 is where x is equal to -1, and my normal vector here has the vector components -1, 0, 0. S sub 2 is where x is equal to 1, and my normal vector has components 1, 0, 0. S sub 3 is where y is equal to -1, and my normal vector is the vector with components 0, -2, 0. S sub 4 is where y is equal to +2, and my normal vector has components 0, 2, 0. S sub 5 is where z is equal to -3, and my normal vector has components 0, 0, -3. And S sub 6 is where z is equal to 3, and my normal vector has components 0, 0, 3. If I look at f dotted with n for each side, f dotted with n for side 1 gives me -1, and f dotted with n for side 2 gives me +1. Likewise, f dotted with n for side 3 is -2, f dotted with n for side 4 is 2, for side 5 I get -3, and for side 6 I get +3. If I add up all these divergences for all of the faces, my net flux is 0, and this agrees with what we found when I computed the volume integral. So now you get to try it. Pause the video and evaluate both integrals in the divergence theorem for the vector field given by f is equal to a vector with components 2x, 3y, 4z, where D is the set of all points x, y, z, such that x squared plus y squared plus z squared is less than or equal to 4. Check for consistency when you compute both integrals, and when you're ready, restart the video to check your understanding. I want to compute the volume integral first, and we need to first compute the divergence of f. The divergence of f is f sub x plus g sub y plus h sub z. For my vector field, this gives me 2 plus 3 plus 4, or 9. My triple integral over d of the divergence of f dv is the triple integral over d of 9 times dv. The 9 can factor in front of the triple integral, and I'm left with 9 times the triple integral over d of dv. This is just 9 times the volume of a sphere of radius 2. So I simply use my formula for the volume of a sphere with radius 2. I get 9 times 4/3 pi times 2 cubed, and I get 96 pi. Now I want to compute the surface integral. I'm going to need to parameterize my vectors first using the standard parameterizations for a sphere of radius a. My parameterized vector field f is given by a vector with components 2a sine u cosine v, 3a sine u sine v, and 4a cosine u. My normal vector becomes a vector with components a squared sine squared u cosine v, a squared sine squared u sine v, and a squared cosine squared u sine u. F dotted with n will give me 2a cubed sine cubed u cosine squared v plus 3a cubed sine cubed u sine squared v plus 4a cubed cosine cubed u sine u. Our region D gives me an a of 2, so that f dotted with n is equal to 16 sine cubed u cosine squared v plus 24 sine cubed u sine squared v plus 32 cosine cubed u sine u. Now I need to compute the integral piece. The double integral over s of f dotted with n ds is equal to 8 times the double integral over r of 2 times sine cubed u cosine squared v plus 3 times sine cubed u sine squared v plus 4 times cosine cubed u sine u dA. I can write this now as an iterated integral. and I get 8 times the integral from 0 to 2 pi of the integral from 0 to pi of the quantity 2 sine cubed u cosine squared v plus 3 sine cubed u sine squared v plus 4 cosine cubed u sine u du dv. I compute that integration piece and I get 96 pi, which is exactly what we got when we computed our volume integral, so that the results are consistent. This is how we can use the divergence theorem to work with vector fields in order to find the flux across a boundary. Be sure and let me know if you have any questions.